Unmanned Marine Vehicle for Disaster Management. Abstract. The idea of the project was inspired by the floods in the state of Maharashtra in year 2019. The aim of the bot is to provide essential commodities like food, clothes, and first aid in areas where human help is inaccessible during flood situations. Also, the bot would be instrumental in reducing the workload on the emergency services as it can be controlled by one person only. During floods, it becomes difficult to reach out to each and every flood-affected person. In such situations, a remotely controlled vehicle can be of immense help for the aid to stranded people. Unmanned Marine Vehicle, UMV, can serve the purpose by swiftly detecting stranded people and providing them the necessary help. It can be controlled remotely and detect the stranded with help of the camera mounted on it. ACFD analysis, calculations for buoyancy and turbulent forces in water were performed. The UMV was put under a short testing period in which all its essential functions were tested. This UMV will help in flood situations to supply essentials in the least time possible and also to relieve the authorities by reducing manned risks. Keywords: automation, disaster management, essential commodities, UMV, remote unreachable areas. Introduction. Unmanned marine vehicles are used to simplify transportation of food packages, first aid, and other basic commodities to flood-hit people. The basic components of this vehicle are the load-carrying unit on which the load to be carried should be placed. The load-carrying unit is attached to the motor unit. 4 motors are placed in this unit which power the propellers which provides motion to the vehicle. The 12V battery is connected to the motor driver then connected to the propellers. The HC-05 Bluetooth module will control the direction of motion. This helps the vehicle to move in a particular direction. With the help of ESP32 camera module mounted on the vehicle, the operator can maneuver the vehicle accordingly. Components of unmanned marine vehicle are a chassis used for mounting of electronic components and carrying the payload. Main goal while designing it was to have a good load carrying capacity and sturdiness while keeping the relative density lesser than water for it to float. B motor housing unit. It is used for mounting of the motors in such a way that maximum power is developed to run the propellers. C battery, 12V, power the motor through the motor driver and supply the power ESP32 camera for live streaming. D Arduino Uno controlling the ESP32 camera and the motor driver. 2. Design for unmanned marine vehicle. The design for the bot was done in SolidWorks software. A material selection for the chassis of bot. The material chosen for the chassis of the bot is aluminum in the form of sheets with thickness of 0.0015 m. Advantages over other materials. High strength, so it can easily carry the load. Manufacturing processes are easier. The relative density of aluminum is less as compared to other metals. During 3D printing, less infill should be used to reduce relative density. Also, it's a relatively expensive method, so we selected aluminum for our load carrying unit. Also, it can tolerate water shock waves. A motor housing body. The motor housing should be able to accommodate 4 DC motors. The selected material for the body of motor housing was polylactic acid, PLA, and was manufactured using 3-dimensional print. The curves and structure of housing was such that it could be difficult to manufacture using sheet metal. Advantages of PLA. PLA is ideal for 3D prints due to its lower printing temperature and is easier to print with and therefore better suited for parts with fine details. Moreover, PLA provided better and enough strength as compared to other material. B. Propellers. The selected material for propellers was polylactic acid or polylactide, PLA, manufactured using 3D printing, with 50% infill. 4 propellers were coupled to each DC motor for the required motion over water. 3. Methodology. A system of electronic components is built to supply the battery power to the motor according to the operator. For maneuverability, the power should be supplied to the motor in a specific manner. The UMV moves on the water. A device is required to find people in unreached areas which will guide the operator of UMV exactly where to move. Components required are a ESP32 cam. The ESP32 cam is a very small camera module with the ESP32S chip. It comes in 2 parts. The main board, which is an ESP32 module mounted on a larger board, and a separate camera module. Camera is of 2 megapixels and the whole unit requires about 5 volt power. It is provided with a micro SD card slot which is beneficial to capture and store images taken with the camera or to store files. It has an IP address which can be copied and opened in the browser for live streaming. Thus, ESP32 camera is used for live streaming through the prescribed IP address. Fig. 4, ESP32 camera module. B. Arduino Uno. The Arduino Uno is a microcontroller board. It has 20 digital input/output pins, out of which 6 can be used as pulse width modulation outputs and 6 can be used as analog inputs, a 16 MHz resonator, a USB connection, a power jack, an in-circuit system programming, ICSP, header, and a reset button. It is used in UMV to receive the commands from user through Bluetooth module, process, and accordingly control the power supplied to the motor through motor driver based on the code which is fed to it and also for the image processing of camera module. HC05 Bluetooth module. HC05 6-pin wireless serial Bluetooth module is a Bluetooth module used with microcontrollers such as Arduino Uno. It uses the UART protocol to make it easy to send and receive data wirelessly. It is used in UMV to receive commands from operators. D289N motor drive. It is a high-power motor driver perfect for driving DC motors and stepper motors. It uses the popular L298 motor driver IC and has a 5-volt regulator which it can supply to an external circuit. It can control up to 4 DC motors, or 2 DC motors with directional and speed control. Motor drive is used for controlling power supplied to 4 DC motors in UMV which helps for maneuverability. Miscellaneous. 12-volt battery as power source and 4 300 RPM DC motors for providing UMV required motion. Fig. 5, Motor Electric Circuit. 4. Analysis. By knowing quantities such as maximum velocity of the bot, dimensions equivalent to submerged bot, frontal area of bot we can get following results with help of simulation tools like ANSI. A. Flow characteristics. B. Resistive force. C. Velocity profiles along the width of bot. D. Understanding of propeller position. Overall flow conditions in terms of velocity. The above figure gives an idea of change in velocity and flow separation due to corners in the model. The flow can be improved by more streamlined design which will further improve the efficiency. Flow characteristics at the center of the model. From the above figure, the flow divergence is visible through the analysis. Also, the observation about the minimum fluid availability at the center is considered for location of the propellers. Flow characteristics at the inner edge of protrusion. Protrusions are the I-shaped extensions part of the load-carrying unit of the UMV. The analysis at the protrusion is necessary as they are the features experiencing the resistive force first while moving ahead. The inner edge characteristics help us to get a better understanding of flow. Flow at outer edge of protrusion. The above analysis is important with respect to the propeller system. The distance of the propellers from the center has to be in the region where the flow of water is least affected. Also, in order to maintain the compactness of the model, the propellers should not be extremely wide owing to the better flow conditions. Fig. 10, Flow at 25 mm distance away from outer edge of the protrusion. Flow at 55 mm distance away from outer edge of the protrusion. The need of analyzing above flows is to understand when the flow becomes normal and hence the position of the propellers can be placed for having maximum propulsion efficiency. The resistive force of 45 Newton was obtained and is used for the calculations as below. Considering the iterative calculations from above CFD, the range for resistive forces was found. This range will help us calculate the viscous drag the model is experiencing in the water. As the drag remains nearly constant for a range of velocities of the model, this value of drag can be used to calculate the forces experienced by the model in the water at different velocities, which will help in deciding the power requirements of UMV, i.e., the motors which need to be used, and designing the model. A MATLAB code was generated to plot the graphs of resistive force versus velocity at different values of drag coefficient. The top speed of the UMV is considered to be 5 km per hour. Viscous force resistance in newtons against velocity in kilometers per hour considering drag coefficient as 5. Viscous force resistance in newtons against velocity in kilometers per hour considering drag coefficient as 6. Viscous force resistance in newtons against velocity in kilometers per hour considering drag coefficient as 4. For maximum drag coefficient 6, the maximum resistive force generated is 142.2 N. Motor should be selected to overcome this resistive force at 5 km/h to propel the bot forward. Power required to propel is given by force multiplied by velocity, i.e. 196.23 watt, 142.2 *13.8. 7. Conclusion. The prototype was tested in the water tank with 1000 gm of test weight and results were promising according to analysis and calculations. The final design is a stackable structure for easy portability with a lightweight body for good buoyancy. Central U-shaped chassis with propellers and camera mountings will help to navigate and detect the stranded people and necessary supplies can be provided to them. However, the prototype can be modified by using gyroscope and direction control devices so that it can be operated in turbulent flow. Hence, we can modify the prototype so it can sustain under extreme flood conditions. Using waterproof roof frame and enclosing the prototype in such a way so that it will get protected from floating debris or side impact can also be done for better results. 8. Acknowledgement. This work is partially supported by the Department of Mechanical Engineering, Vishwakarma Institute of Technology, Pune, Maharashtra. We offer our sincere gratitude to Professor Mukund Kard who guided and supported us.